Okay, so again, no, welcome back, no, to those of you who just entered, no. We are kind of cut once in a while, no, but anyway, no, we will be continuing this, no. So this is still our series of lesson. Part of this is on capacitance still. So we just completed part 2 of our lesson, no, on that's part 2 of our lesson on capacitance, no. So we will just discuss in passing, no, this thing that we call as the electrics. So in lesson 3.1 we mentioned about, no, factors that affects capacitance, the circuits, no, parallel and series connected capacitances, how they affect, no, the total capacitance, the charge, the voltage, no, in the circuit, no. So we already make mention of a very simple circuits of series and parallel connections, no. Now we will be entering next, no, after we discuss, no, very briefly probably the lesson on the electrics. We will go into moving charges already, huh? Can I just see some thumbs up, please, no, if you are hearing me? So we have, guys, no, dielectrics. So let me open this, no. So for our topic or lesson today, no, on dielectrics, which we will not really stay long, no. And of course 3.2 there, no, on energy and the electric field of a capacitor. We uh, did not, no, include that one anymore, no, because basically, no, we will be going into, no, current, no, the lesson on resistivity, resistance, no, in the moving charges nga lesson, no. Now but somehow, now let's just take this up, no, this concept about our dielectrics, no. So dielectrics again are, or capacitors I mean, no, these are devices that can store electrical energy, no. We realize now again, if you were able to see the simulator, no, we can store there enough charge, no, in a capacitor, and somehow once the capacitor is fully charged, we are able to light up a bulb, no, just like it is similar to a battery, no. But somehow as the charges inside the capacitor, no, is drained or is used, or maybe, no, is discharged, then the light, no, that comes from the battery, or the light that comes from the bulb eventually glimmers, and then eventually, no, it fades away, no? So again, no, the goal or the main thing about, no, our, no, capacitor, no, they can be used in photography, no. There is a capacitor in a portable photo flash unit. So you notice that some bright light, no, requires probably enough charge that, no, it has to discharge that charge in the capacitor, no. So you can produce, no, a very bright light, no. But that very bright light in the flash of a camera does not really last long, no, in some of the cameras that you've seen, no. So it provides, no, a better image of the picture. So again, no, because the charge can be stored temporarily, no, in a capacitor, no. So capacitors are, no, very crucial. Now again, one thing that influences or adds to an increase of the capacitance is the presence of a dielectric. And a dielectric again is a piece of an insulating material, no, that fills the space between the plates of a capacitor. So if you recall your parallel plate capacitors, there's a gap there in between. And if you don't fill it with anything, it is filled by air, no? So sanghangin, no? Now, they find out that the air there can serve also as an insulating material, but if you really put, no, another insulating material na solid, they discover that they can also, no, improve the capacitance value of a parallel plate capacitor, no? Now, examples of these insulating materials are, no, mineral oil, plastic, mica, porcelain, no, and many other, no, insulating, or sometimes, no, metalloids, no, na pwede mo mabutang, no. So germanium, silicon, these are I mean, no, these are semiconductors, no. they act like a conductor, and they also act like an insulator at times. No? So again, now when you insert this not to your capacitor, then you'll probably increase the capacitance of the capacitor depending on the material or dielectric that you actually use. No? So basically, that's the significance of a dielectric. So a dielectric, again, is a material that is able to be charged. No? And again, most of them, or if not, all of them, are insulating materials. So I think now that's the main focus lang that I will just draw out out of this 3.3 lesson. No? Now let me proceed or go to a topic on moving charges already. No? So this time we are not dealing anymore with charges that are at rest, which are electrostatics, and we are going into a topic already on moving charges. And when charges eventually flow, we have what we call a current. So in these wirings here above, these are crucial to our daily living. We enjoy and we have our convenience at home because whenever we want to cook, we have a lot of convenience, like when we want to beat the egg. So there's an egg beater there for your cake whenever you want to bake. So if you don't have an egg beater or a beater there, then you will have to mix your baking material manually. So again, the importance of this moving charges. So what makes electric charges flow? Again, there must be some kind of a potential that will try to push them. We know that we cannot enjoy the benefits of electric charges if they are at rest. They have to be moving for us to be able to make use of their stored energy. How do charges flow? What are electric currents? So again, when charges eventually flow, we will encounter next a term called electric currents. Okay, and then we will go next to the term called electric current. Now, in order for charges to flow, we really have to understand that there must be a presence of there must be a conductor. So if this is a conductor, guys, a wire, for example, then if you provide this wire with some electrons, and again, the electrons are able to enter through this, through this portion of the wire, so perhaps you can have some small charges there, so these are now our charges. Maybe they are electrons, now when they start to move, then again, that's the time that you will have a current already. So when this charge eventually start to flow, so a moving charge is called as a current. So or other words will be another word will be electric current. Now they describe electric current, or they give a symbol for the electric current as letter I. And the unit, the unit that they attach to electric current is this thing we call as an ampere. So what is a current again? So this is the rate. They describe it as the rate of flow of electric charges. Electric charges has to, again, be moving in order for you to have an electric current. They have to really travel. So if they're merely accumulating in a piece of insulator, then you could never call that as electric current. There must be a continuous flow of this no electric charge. No, again, no, how fast or how good they are moving into no this wire no depends on this conductor. No, there are materials that are really good conductors, and again, no, there are materials that are no poor conductors. No, now, usually good conductors of electricity are also good conductors of heat, and metals are usually no mentioned as good conductors. No? So again, no, charged particles flow in the ionized gases of fluorescent lamps. They flow through semiconductors, in car batteries, no? In packet calculators, and in chips, no? Sa mga circuitry. No? You see some kind of a circuit. So these circuits or these uh, integrated circuits no? Controls your microwave oven. Maybe it also controls your car. No? But then again, no, there has to be no a flowing charge in these devices. No? So an electric current again. No? So an electric current has to be no done with a continuous flowing of charge. No? And this continuous flow of charges probably no, was possible when something like a battery was created. And Alessandro Volta, this I think he's an Italian guy. He invented the battery. No? So when he invented the battery, then the battery was able to let no charges travel no nga sige-sige no continuous no. Now we can also let capacitor no move charges, but again no temporary lang gid no on a very short no period of time only. No, that's possible. No, again no, so currents are no an idea no of the flow of these charges. No, so you need a conducting wire, a conductor no in order for currents to eventually flow. No? So here's again no, a diagram of our battery. No? So the long line no, is known as your positive side. The shorter line is known as your negative side. And then the way the charge is flowing is from higher potential to lower potential. No? Again, no, if you're considering a positive charge, no? They call it as a positive charge whenever it is moving from positive to negative. Now, when it is an electron again, it will be moving from lower to higher potential. No? So it's a different direction whenever you are dealing with no, with an electron charge. No? Because we know an electron is a negative charge. No? Okay, so some electrolytic battery. No? So electrolytic battery is the one that you have in your car. No? If you have your car there, no? If you notice it, no? We call it as a wet cell. And the one that you buy in SMCT, the one that pack, no, are called dry cell. Yung mga daw cylindrical, very small cylindrical batteries. But however, inside your car battery, no, you have a liquid there called an electrolyte. No? Usually it's made of acid. No? So it's wet cell because you are putting no, some amounts of acid, and there are electrodes there or metals no, that you place in between the acid, so the metals no, will gather the ionized no, particles in the liquid. No? So the ions in the liquid will concentrate on the electrodes, and once the electrodes have two opposite no, charge, then an electric field is set up, and then therefore now there is going to be a potential between the plates. No? So that's how we consider no, the uh, this electrolytic battery. No? So we call the liquid inside as an electrolyte. No? So usually it's made of an acid. No? Now, some metals that are inserted here could be zinc, no? And there must be another metal on the other end. No? Pwede man nga lain siya nga metal. And then therefore, no, you will now have an electric potential in between your electrodes. No? So we call again the electrodes here as your, I think, no, the cathode and the anode. No? So charges eventually when they flow, now we call that one now as our no electric current. No? Now what are the factors that affect now how fast or how slow charge move no in our wiring? No? So what affects the flow of the charge? No? I think the one that affects the flow of the charge is your resistance no, in the wire. No? So again, no, the rate of flow of the electrons is known as your no I. No? I is representative of the electric current. No? So that's the way we calculate I is that if we are to use no knowledge in knowledge in calculus, no, so you have your derivative of q all over the derivative of the time, no? dq over dt. So basically that's what we have as the rate no of the flow of the charge. No? So it is always per unit of time. No? Or others would write I as q divided by the time. No? Or ang value sa aton gali nga charge q could also be the product of I times time. No? Again, our value q here is the charge. Then you have your current I, no? And the last value there is your time. No? And usually the time is in seconds. No? So Q is coulomb, time is second. So coulomb per second is known as ampere, no? The unit of our current. So kung ano kadasig ang pag-flow ng charge, amo na ang ginatawag natin nga current. No? You know, here's an example of an ampere in terms of the unit that we are actually using. No? Okay, we are going next, I think, to another topic no, on resistivity. No? So let me mention about no, a discussion on resistivity. Do you have a question, by the way? Okay, so we will go next to this idea of resistance. No? And maybe now we will mention about this concept of what we call Ohm's law. No? So we will now go into another characteristic in the wire. No? Now, if you will deal with wirings, guys, no, if you will have some wirings, maybe a wire that is big, no, dako iya cross section, and then you could also have a wire na gamay ang cross section niya, no. So they are both copper, but one copper wire is having a huge cross sectional, no, and then the other one, no, medyo gamay ang iya cross section. No? These are two different wirings. No? Now, these wirings, again, amo ni ilang cross-section. No? Now, there's also a need for you no, not to use very big wires. No? Because if you are trying to connect a light there, no, your terminals of your light bulb no, does not require you to use very thick wires. No? You have to have a light and a thin wire no, for you to connect your proper device. No? So there's always a use for the sizes, dimensions of the wiring. No? But somehow, no, when these wirings no are varying in their area, they have they will eventually affect the thing we call as resistance. No? So allow me to call this shaded or this line no part of the wire as cross-sectional area. No? So we call it the cross-sectional area. And then there's also this thing that we find in our wire, and maybe we can call this as our length. No? So our wire may have some short, some longer lengths. No? And again, no, the factors no, that probably no, are crucial in the thing that we will try to name no, called as resistance. Now, resistance is called as the opposition to the flow of the electric charge. No? If we have friction, no? If friction is familiar no, in our mechanics or in our lesson on motion, in wirings, no, the one that will try to make the charges flow slower or faster is this thing we call as resistance. No? So resistance of a material is operationally defined no, in this way. So there's this thing called V over I. And I think this V over I thing is known as the Ohm's law principle. No? But again, no, that's how they describe R. No? So R is denoting no, this variable called resistance. No? Usually that's how they label no, the resistance. No? So the value V is your value V there is your voltage, I is your current. No? So somehow the resistance is affected by the voltage and the current. So if you divide the voltage of the wire by the current in the wire, you'll get the resistance. No? But somehow the more current that you want to flow in the circuit, then dapat there must be lesser resistance. No? Because somehow resistance and current are inversely proportional. No? So if V divided by I is R, then we'll see that resistance and current are in inverse no in their relationship. No? So we will see that greater resistance means lesser current. No? So but what affects this resistance as well? No? So if we are thinking about wire, what we usually find no, is that the resistance R no, is also no, directly proportional to the length, no? To the length of the wire, which we call as L. No? So R and L are directly proportional. Longer length has higher resistance. No? However, another relationship is that of cross-sectional area. So if length there is L and cross-sectional area is A, no? Ang mga wiring ko nung dalag ko gali iya, no, ang dalag ko area ng wire no. Ang ato naman R no is inversely no proportional to the area no? Area A. No? So meaning if the area is wider, less ang resistance no. Okay, sorry, no nautod siya no. So let me just rewrite this somewhere else no. So ang R naman no, again R is again no inversely proportional to area A. No? So no? In terms of R, no? So sometimes they write it as like this. So R is they equate it. No, if they equate it, then that's in terms of a constant K, and then it is proportional to length, but no, it is inversely proportional to the area. No? So K there is a value which we call as a constant. No? But somehow they call the term there K. K here is called as the resistivity. No? So they use a term there, resistivity, to denote the value of the resistance. No? So K is the resistivity, and usually now since a lot of symbols are using K as constant, that to distinguish it from other constants, let us use instead this omega symbol, or this rho symbol. So this is your expression for the resistance, and we write a symbol rho, so letter P na ang tsura sang rho, which again, which we replace the symbol K there with this rho. So muna ni siyang atong ginatawag karon nga resistivity ining rho. Again, the resistance is affected by, again, the length of the wire and its cross-sectional area. And likewise, that resistance is also affected by the voltage in the wire and the current in the wire also. But this equation is known as Ohm's law. This one is simply the resistance of a particular wiring.